All right, so a heating curve just means the graph that you would get if you are going to be measuring the temperature over time. So in the lab, you would take any substance in its solid state, and every time you notice changes happening where it started converting from a solid to a liquid, you would record those spots. And then you watch again, and then when it starts going from a liquid to a gas, you would record those temperatures, and then you would connect your dots. So every phase diagram is going to look like this. That first flat line, that's your melting point. Your second flat line, that's your boiling point every single time. Okay? That means the diagonal line, that's when it's a solid. The second diagonal is when it's a liquid. Third diagonal is when it's a gas. So this part, when it's going from a solid to a liquid, that's when it's melting. This is when it's going from a liquid to a gas, and that's when it's boiling. So those phase changes in there are important, and if you notice, they don't change temperature. The whole time it's melting, it's staying at the melting point. So that's why we have to use a different equation for those guys. Okay, so whenever you're on the flat lines, you're going to use N delta H to calculate the heat. And anytime that you're on the diagonal lines, solid, liquid, or gas, then you're going to use Q equals MC delta T. So you got to decode where you are in the problem to know which equation to use. Okay, we're going to have benzene, ethanol, and water. So on each of those, in your notes, write down all the points in the chart that it gave you, melting point and boiling point, so you know those spots. The C values, because that's the specific heat. Benzene has a different specific heat when it's a liquid than when it's a gas. And that makes sense, right? Because it spreads out more when it's a gas, so it should have less. Delta H of fusion is when it is fusing or it's becoming a solid. Okay? So that is the number that we'd use when we're melting. Delta H of vaporization is when it's boiling. So that is what we'll use when we're boiling. So anytime you are deciphering this and they ask you for the phase change heat for boiling, you would use vaporization. Fusion, you would use for melting points. So now that we have that all broken down, then let's figure out some things. I'm going from a solid to a liquid, solid to the liquid. That's that guy melting. So I'm going to have to use flat line, the N delta H equation. N delta H. And what else do I need to know? My delta H that I use for melting is heat of fusion. .9 kilojoules per mole. Now everything we're doing for benzene is at 1 mole. 1 mole. So my Q is equal to 1 times 9.9 kilojoules per mole. So that's going to give me 9.9 kilojoules. Okay. Now, in my liquid phase, that's just when it's a liquid. So that's between the melting point and the boiling point. I have those numbers. It's a diagonal line, so I'm going to use Q equals MC delta T. Q equals MC delta T. But wait, I don't have a mass. I only have moles. That's okay, because benzene is C6H6. So that's 6 times 12.01 plus 6 times 1.01 that is going to give me 78.12 grams per mole. I got the 1.01 from hydrogen's mass, and I got the 12.01 from carbon's mass. So my Q value is equal to M, 78.12. My C, when it's a liquid, 1.74 joules per gram degree C. And my delta T is those two temperatures, boiling point of 80.1 minus melting point of 5.5. Okay, so 80.1 minus 5.5. And that answer times 1.74 times 78.12. I'm going to have 10140.3 joules. How many sig figs? 3 sig figs, 2 sig figs. So 2 sig figs. 10000, 10,000 joules. Okay. Notice this guy is in joules, and the one before is in kilojoules. So if they ever ask you to add things together, make sure your units match before you add them. Liquid to gas is next. Liquid to gas means the phase change at the boiling point. We use N delta H. What delta H do we use? Delta H of vaporization, because that's what we use for the boiling point, because we vaporized it. N delta H. How much was it? It's still 1 mole. We didn't take any of the benzene out, so the whole problem uses the same grams and the same moles. 30.77 kilojoules per mole is the heat of vaporization. So 30.77 kilojoules is my liquid to gas number. How about if they just gave me 2 sets of numbers, 90 to 100 degrees C? Well, I gotta look and see where it is on the graph. 90 is above the boiling point of 80, so that we're up in the gas area for that. Still use Q equals MC delta T, but our C value has to be the gas C value. Q equals M C delta T. What is my mass? 78.12, because 1 mole is 78.12 grams. My C value is the gas one, 1.04 joules per gram degree C. And my delta T is 100 minus 90, which is 10. So 10 times 1.04 times 78.12 gives me 812. Now I only have 1 sig fig here, so 800 joules. So that's how we do all the different parts.